So now that we understand when we're allowed to multiply two matrices together and what we're supposed to produce when we multiply two matrices together, let's see how to actually do it. So remember, in order to multiply two matrices together, we have to be in a situation where those matrices fit into a diagram that looks like this. So again, to recap, when we are writing a diagram like this, all we're communicating are the shapes of the various matrices. So we need B to be an M by N matrix, and we need A to be an L by M matrix. All that's to say that we need A to have the same number of columns that B does rows. And when we multiply these two matrices together, we'll produce a new matrix, A times B. The number of rows will be the same as the number of rows of A, and the number of columns will be the same as the number of columns of B. Okay, so here's the first formula we'll learn for doing this. We're going to learn two different formulas that produce the same result. This one is what I like to call the column perspective on matrix multiplication. So the idea is that if we're in a situation where we're allowed to multiply a matrix A by a matrix B on the right, the formula for doing this says, let's look at each individual column of the matrix B. And then the compatibility criterion says we are allowed to multiply each one of those columns of B by the matrix A using a matrix vector product. So since A is an L by M matrix, and since B is an M by N matrix, each column of B is a vector in Rm, which means we can multiply that column of B, every single column of B, by the matrix A, and we produce a new vector that lives in RL. So we list each column of B, we multiply A by each of those columns, and we store all of the new vectors in the columns of a new matrix. So this is, of course, where all these vectors B1, B2 up to Bn are the columns of B. Great. Okay, so let's see how this works in practice. So here we're in a situation where we want to multiply this 4 by 2 matrix by this 2 by 3 matrix. Of course, we're allowed to do this because, again, if we want to view this diagrammatically, when we take a matrix A and multiply it by a matrix B, we're trying to build a machine that would go through B and then through A. B is 2 by 3, which means B goes from R3 to R2. And A is 4 by 2, which means A goes from R2 to R4. The number in the middle matches up. And when we do multiply these matrices together, we should produce a machine that goes from R3 to R4, which really means that we should produce a 4 by 3 matrix. Well, how does that work here? According to the column perspective we just introduced, the idea says, well, I should just multiply A by each individual column of B. And remember, the way matrix vector multiplication works says when we multiply a matrix by a vector, we take a linear combination of each of the columns of the matrix we're multiplying, where we're using the scalars that are coming from the vector. So the first thing we're going to do here is recognize, well, when I multiply this 4 by 2 matrix by this 2 by 3 matrix, I should end up producing a 4 by 3 matrix. So all of these entries are currently empty. And how are we going to insert numbers into this matrix? Well, the first thing we'll do is we'll take the whole matrix A on the left and multiply by the very first column of B. We'll record the result in the first column of the matrix we're building. Now, the first column of B is 1, 1. So how do we take this matrix A and multiply by the column 1, 1? Well, really what this is saying is that we should take 1 times the first column of A, and then 1 times the second column of A and add them together, which is really just to say we should add the two columns of A together. So the result should be 1 plus 2, which is 3, negative 1 plus 1, which is 0, negative 1 plus negative 3, which is negative 4, and 0 plus 4, which is 4. So that's the first column of our new matrix. What about the second column? So now we're going to take our matrix A and multiply by the second column of B. Again, we're producing a linear combination of the columns of A, where the scalars we're using are coming from the vector we're multiplying by, in this case, the second column of B. And those scalars are 0 and negative 5, which is really saying scale the first column of A by 0, so If we wanted to, we could just ignore the first column of A. And then we scale the second column of A by -5. So all we're doing is we're multiplying the second column of A by -5, which should give us what? -10, -5, 15, -20. So that's the second column of A times B. What about our last column of A times B? Well, now we're going to take the whole A and multiply by the third column of B. That third column has entries 1 and -1. So really what we're going to do is we're going to take the first column of A and subtract the second column of A. So we should end up getting 1 minus 2, which is -1. Then we'll get -1 minus 1, which is -2. Then we'll get -1 plus 3, which is 2. And then we'll get 0 minus 4, which is -4. So now we've successfully built the whole matrix product. A is 4 by 2, and B is 2 by 3. So right away we know we're allowed to multiply these matrices together because the number of columns of the matrix on the left is the same as the number of rows of the matrix on the right. And then once we multiply these two matrices together, we know that we'll build a 4 by 3 matrix. And this column perspective says we can build the columns of this new matrix by taking the matrix A on the left here and individually multiplying by each column of the matrix B. Here's a second example just to illustrate the formula again. So here what's happening is somebody is handing us a few equations. Here we have two matrix vector products that are given to us. The matrix A, which in this case is 4 by 3, multiplies by this vector B sub 1, which is 1, -1, 0, to produce this particular vector, -1, 2, -2, 0. And then the same matrix A, which again is 4 by 3, multiplies by this vector B sub 2, which is 0, 2, 1, to produce this new vector, -1, 0, 0, 2. Well, all of these two equations could be more succinctly written as one equation. What we're doing is we're taking the same matrix and we're multiplying it by two different vectors. So another way to communicate this information is to take those two vectors that were originally given, B1 and B2, and insert them into the columns of a 3 by 2 matrix. And the fact that someone has told us what these matrix products are, or what these matrix vector products are, allows us to just immediately say what the product of A and B will be here. Remember, in this case, A is 4 by 3, and B is 3 by 2, so we should end up producing a 4 by 2 matrix. The first column of this product is whatever we get when we take A and multiply by the first column of B, which we are choosing to be the first vector B1 that we're given in these equations. So I know that the first column of this product should be the vector -1, 2, -2, 0. What about the second column? Well, to get the second column, we're using the second equation that we were handed from the outset here. That's to say, we should take the matrix A that we're working with here, and then multiply by the second column of B, which again, we chose to be the second vector that we're given in the start of this example here. And we could either redo the matrix vector multiplication ourselves, or we could just record the result that we're given. We know that the second column of this product will end up being -1, 0, 0, 2. So that goes here.